So let me recall the problem, the formulation of the problem we have seen yesterday. So I had two variables. One is this deformation field, so 2 by 2 matrices, which for the moment I simply assume is L1. And then another one is this set, which is a closed set in omega, which actually contains the support of the curl of A, which I assume to be a measure. Okay, so curl of A in the distributional sense is a measure. So this is somehow the local deformation of my crystal, and this is the set of possible incompatibilities that are present in this crystalline structure. And so the energy, the corresponding energy is an energy which depends on a small parameter, depends on A, S, and say on the domain omega, and what is the eraser? Oh, here. And this is made of two terms. One, which is the elastic energy, which is outside what I will call the core of the incompatibility. So an epsilon neighborhood of this set S, I take the simplest elastic energy I can imagine. So something that looks locally like the one that Pascal was showing today. So locally is a gradient, the integral of the gradient with this energy density. And then there is another term that accounts for the fact that here I'm removing sort of the energy of the interaction of the atoms which are next to the incompatible set. And so I very roughly account for it, taking the measure of this set. Okay? Okay, yesterday we have seen that with very simple configuration, for instance, taking a rigid configuration like rigid rotation by given angle on half of the square of sides L and rotation by the minus that angle on the other half, I get an energy which is of the form L times epsilon. Okay, so I simply put this configuration over there, and I realize that this energy is over there L epsilon. So essentially, I'm saying that this energy will scale as epsilon when epsilon represents somehow the lattice parameter, scale as epsilon, and like the length of the sort of interface I expect to see in this type of configuration. So we stop. Sorry, it's the inclusion is the other way around, sure. I was about to write this and then I move it. Sorry. So we stopped here. So with the idea that we want to give an asymptotic expansion for the minimum of this energy when you look at this energy on a cube of sides L, a square of sides L, with the condition that at the lateral boundaries of this cube you have this R minus alpha, R alpha as boundary condition. So we want to estimate this this minimum problem, and we expect to have a scale with epsilon in order to get a line tension model. But as I said at the beginning, we really want to see a behavior when alpha is small, which has infinite slope at 0. So, and this is not the case. Here we have just a constant. So maybe we should do something more sophisticated. And the idea is to introduce defects, as I was showing in the initial picture a la Reed and Shockley. And so let me go back to the example of the defects. Which we have seen yesterday, which was this field. So this is just an example, but this field identity plus, so now I will scale it accordingly with my model. So actually I forgot another condition, which is the circulation of my field around defects should belong to, along loops should belong to the lattice scaled by epsilon. And so an example of this field could be the one I've seen yesterday, which is E1 tensor product x orthogonal over x squared, which correspond to have the curl concentrated on a Dirac mass at 0. So yesterday I didn't put the epsilon, but now I'm putting the epsilon because I'm assuming that the Burgers vector has size epsilon. And so this was somehow a way of writing in a continuum fashion a defect like that, a single dislocation like this. So in a domain omega, this will be the point in which you see the defect. So let's see what would be the energy of such configuration. Well, the idea is that actually, when epsilon is small, you have that the A minus identity is almost the distance squared of A from the rotation. So when epsilon is small, you are really close to the identity, so this distance is achieved close to the identity. And so the energy over there, so this is, if you want, 0 in a ball of radius r, would be the integral of this quantity over here, over Br minus B epsilon at 0. And here, instead of the distance, which I have here, I just put this difference. Okay? And so this difference is what is left over here. So it's epsilon 1 over, so it's epsilon squared. So it's the modulus of this squared. So it's epsilon squared dx, right? So this difference over here is that squared, which is this. And now you integrate in polar coordinates, and you get that this is 2 pi epsilon squared log r over epsilon. Right? Yeah, but there was a 2 pi over here. So actually this is the 2 pi squared. In fact, I was confused by this. Okay. In order to have circulation by one single vector. Okay, so in this way the circulation is epsilon E1. Otherwise it's 2 pi. Okay, so a single, so I'm neglecting the second term, which is lower order because it's epsilon squared, right? So a single defect at least with this specific field, behaves like the logarithm of the core region. And this is actually something which is true in general. So here I did an explicit computation, but in general, if I have a field whose curl as a given Burgers vector, which in this case is epsilon E1, but who knows, a given Burgers vector times delta at 0 or in a given point. Now, if I compute the energy on an annulus, so let's put capital R and little r on an annulus of this distant square of A from rotations. As far as I can, if you want, substitute this distance with some more explicit thing, like a square of the field, I can proceed. And so the idea is that I want to be able to say that this field over here is close to a given rotation, which is the same computation that I've done here. So to do that, I need a rigidity argument, which was mentioned by Pascal. So rigidity, well, maybe if you don't mind, I will make a small detour on these rigidity arguments, just to make clear what, because I will use it in several occasions. So Pascal was mentioning the rigidity estimate of Friesiger, James, Müller. So actually this was a result that was proved in 2002, and that is really a breakthrough in the theory of nonlinear elasticity. So it's something that produced a lot of very nice and important consequences. But let me start with I like to go always with a baby example. So what is the rigidity theorem actually? A rigidity result is a quantitative version, so a rigidity estimate is a quantitative version of a rigidity statement. And rigidity is the quantitative version of the statement that says that if a gradient belongs to the set of rotation, then this gradient must be constant. Okay? So the rigidity estimates make quantitative this statement. Okay? And the baby example is the claim that or the fact that if a gradient of a function is 0, then this function is constant. So if you want the quantitative, so sorry, maybe I'm too basic, but the quantitative version of this is Poincaré inequality. Okay? So that tells you that if this is small, this is close to a constant, right? And so, instead, if I want to make this statement quantitative, Friesiger, James, and Müller proved that if, say, omega is in Rd, open Lipschitz, I would say. And then, so there are several different versions. Let me do it in H1, and U belongs to H1 of omega, so that there exists a constant that depends on omega, such that for all u in H1 of omega, with values in Rn, in Rd, and there exists a rotation in S of D such that the distance of the gradient of u from this constant given rotation in L2 is below a constant times the distance squared of this gradient from the given rotations. Okay? So this is the rigidity estimate that was mentioned today, and so it's telling that something similar to what we had here. This was explicit, so this somehow was clear, but this is telling that whatever field I have, if I control the distance from rotation, I sort of control the distance from a given fixed rotation. So, and this is helping here because A is not a gradient in principle, but the curl is concentrated on a single point. So I'm looking at an annulus. I simply cut this annulus and I make it a simply connected domain. And so being curl-free in that domain means being a gradient. So I can remove this cut sigma and simply put a gradient over here. Okay? So now my energy is this one, and so this means that I can estimate from below this energy with a constant, and this constant, I mean, I didn't really tell you this, but this constant you can tell. I mean, these two scale at the same time, the same way, so this constant is scaling invariant. Okay, so it really depends only on the shape, and so in particular here it depends only on the ratio between capital R and small r. Okay, and it degenerates only when they come together. Huh? Okay, so fat annuli have sort of uniform constants. So you can put the constant over here, and well, actually, so and say that there exists a rotation which I call Q here because capital R is already used in SO2, such that with this integral is estimated with this grad U minus Q. Okay? So I'll put A over here, recalling that in fact if I remove the sigma, this is the same as the gradient. Okay? Okay, so now I can again remove the green part, and I'm back to something that is similar to this. So I use Jensen inequality. Well, actually, this computation is done in this context of nonlinear elasticity, but it's the typical computation that produces a logarithmic behavior for fields with topological singularity. So a similar computation is done, for instance, in the context of vortices for Gilbert-Landau that tells you that lower bound, an easy lower bound for the energies of topological defects. So you apply Jensen inequality. So for maybe first you rewrite this in polar coordinates, sorry. So from at the boundary of Bureau of this. And now you apply Jensen inequality, and with Jensen inequality, so you have to divide by the length of this boundary and multiply, and then you apply Jensen inequality and you get the constant, the integral, okay, and then you get the square of the average. So this is 2 pi rho, the square of the average on this ball of A minus Q squared, the rho, right? Now you see that here there is a 2 pi rho, and here there is 1 over 2 pi rho squared. So this is simply a constant of the integral between little r and so there is a 2 pi over there, so similar to that. And then there is 1 over rho times the circulation of this quantity, and the circulation of this quantity is constant, is b. Okay? So there is a b squared, and then the integral of 1 over rho, exactly as we had here. So the log of capital R over little r. So exactly the same computation. So what you end up here, once you substitute the constant circulation, is exactly the result of the previous integral, right? So whenever you have a constant circulation around a region, you have constant line integrals. So essentially you produce this type of behavior for them. So of course the circulation of Q is 0 because Q is constant. Okay, so why did I make this detailed computation? Because I think it's the key point in order to produce the heuristics for this energy. So let me okay, this I pressed it. Okay, so the heuristics which take advantages of the presence of defects is now the following. The idea is that I have my box and I want to introduce many defects, so an array of defects which allowed me to cover the gap that is open when you rotate the two sides, right? So, and so somehow schematically what you do is the following, if you want. You add extra lines like that. So I'll make it, so the idea is the following. I have my domain, which is an underlying crystal structure, like okay, similar here. So which means that you see, I mean, I'm adding this line, this line, this line, and so on. Okay? So each of these lines adds a step of size epsilon, if you want. And now you take these two pieces, you rotate them, and you glue them together, like this. And you end up with the rotation you're looking for. Okay? So this is the idea. The idea is that when you glue these, you essentially just deform slightly the crystal. Then here you glue them, and still you have a small deformation, and so on and so forth. Okay? So this adding this line allows you to have small deformation of a perfect crystal in local regions, plus isolated defects. Okay? So essentially, this is the configuration I am expecting to see in order to achieve this rotation. And so I have to add, so this means that I have to close a gap over here, which is L times sinus of alpha, because I rotate by, well, actually half of it should be that, so I rotate by alpha. Okay, so this is alpha, and alpha is small, so this is essentially L alpha. So in order to close this gap with n defects, I should have that n times epsilon, which is the step, each step is of order L alpha, right? So I have to add n defects. Each of it contributes for epsilon in terms of this length over here. So the difference between this and that is n epsilon, so to say. And this should be of order L alpha in order to rotate and get the angle alpha. And so the total energy of this configuration will be n times, so what is the total energy? Actually, the total energy will be, I'm estimating, if you want, this energy with the energy which I can have in each of these annuli. Okay? So I take this estimate and I put it here. So I have n times these annuli, and the annuli are, so n times, if you want, the energy of a single defect in a ball of radius. So what is this relative distance between defects? And L over n, right? And then I have to remove the ball of size epsilon, which is my core, which is there. And this is n times b squared, which is epsilon squared, times the logarithm of the ratio between the outer radius, which is L over n, and the inner radius, which is epsilon, which is, so is n over L over epsilon. Now I remember that n epsilon is of order L alpha. So this is alpha epsilon, and L over n, L over n, L over n is epsilon over alpha. And so this is log 1 over alpha. There is an L. Sure. No, there is an L here, sure. Yes. So n epsilon, so let me write it here, is L epsilon, L alpha epsilon. It's okay? So I have epsilon, which is the scale I have to use in order to have to rescale the energy to get a meaningful limit. Epsilon, I have the L, which is the length of the interface, and then I have a constant that this is plus lower order terms, and then I have a constant that depends on the angle with the law, which is alpha log alpha. So exactly the Riedenn-Shockley law. So it behaves at 0 when alpha is small with an infinite slope. Okay. Well, this is exactly the theorem. So this is the heuristics, but this is made rigorous by this theorem of Lauteri and Luckhaus, in which they show that, in fact, once you take that energy, so you rescale this energy by 1 over epsilon, and you take the minimum, so this minimum over there of this energy on the cube plus boundary condition, and then you take the lim-inf in epsilon, this as a control from above and below with a law which is of the type Riedenn-Shockley. So they prove a lower and an upper bound for this problem. The boundary condition is again the one I was using above. So they prove the lower bound and the upper bound. The upper bound is a construction, which is done in the specific case of two symmetric angles, and small angle grain boundary with two symmetric angles. And the lower bound produces an incredible and impressive amount of general and abstract results that can be possibly used in other contexts, very deep. So I'm not even trying to give you any details of what is the lower bound, but I will show you how it can be used, or some of the techniques that they use can be used in other contexts, or at least to make somehow this computation even more precise. So in particular, I want to show you another theorem that we proved with Martino Fortuna, a former student of mine, and Emanuele Spadaro, in which somehow we push forward this technique. And in fact, as I said, in Lauterio Lucaus, the constraint is a bit less precise. So it's just that the circulation should be at least epsilon. And this does not make a big difference in the analysis, because they really confine their analysis only to the case in which they have a completely symmetric grain boundary. Instead, we really consider that general model, and we essentially study the asymptotic behavior of this energy. So we define an energy that in principle depends only on the variable A, just minimizing 1 over epsilon E epsilon AS with respect to all possible S that contain the support of the curl of A. In the future, I will use S of A, something which is almost the minimizer of this problem. So if the minimizer doesn't exist, it doesn't really matter, but a good approximation of the support of the curl. Given this energy, we prove a gamma convergence statement. Okay, so we first prove a compactness statement, which is the one for which I will give you more details. So we prove a compactness statement, which is the following. So if we have a sequence with equibounded energy, then up to subsequences, we can prove that this field A outside the coregion, inside the coregion we don't know anything about A, because the integral doesn't see what happens inside the core. And this converges L1 to a field A. Okay, this is a very mild information. It converges A1 to L1. But the important information is that A is in SBV0 of omega with values in S2. And I recall you that SBV0 means essentially that is a BV function which only contains the jump part. Only jump part. So this means in particular that the absolutely continuous part of the gradient is 0. So I'll give you some details, some hints of how to prove this. And then once you have this, you realize that this is the domain of your gamma limit, and you prove that this energy converges to in the topology described over here, converges to a functional, which is actually defined in this space, and it is of the form that we have seen yesterday. So it's a line tension energy which depends on the traces of A on the two sides of the jump, possibly on the orientation of this jump set. And this energy, and say psi, satisfies the Reed and Shockley bounds. So I'm not going to rewrite them, but it means essentially that it behaves like A plus minus A minus log of A plus minus A minus. Okay? So when the rotations are close to each other, the behavior is like the Reed and Shockley law. So it's super linear at 0. Okay. Okay, so what do I want to tell you about this result? Maybe I'll try to give you some ideas of the main. So no, I'll leave this. So some ideas of the main steps for compactness. So the other ones are a bit too. So main steps. So the reason why I want to show you the compactness is because I think it's an argument that can be in general used in, or at least it's instructive because it's a general argument. For instance, it's a general way of using the quantitative estimates. So it makes a bit more clear why, for instance, this Frieseke, James and Müller was so important, was a breakthrough, because it clarifies, so which is somehow the same reason why Poincare inequality is such an importance to get well-posedness, for instance. But in this context of nonlinear elasticity, maybe it's less common. Oh, that. Okay, so these are, I have three main points, main steps. So the first one, so I start with a sequence which is of this form. So it's my field, which has equibounded energy, and the almost optimal set of incompatibilities. So the first step is a refinement. Okay, this is a bit technical. So it's a refinement of this sequence. So instead of this sequence, I substitute this sequence with another sequence. Which has good property, which is close, so such that this field A tilde is close to A, and close means L1. So I will prove convergence for this field A tilde, and I will get convergence for this field A because they are close in L1. And then the new set of incompatibilities contains the old set of incompatibilities with good properties. And good properties, who knows? So I hope I will have time to tell you exactly, but, but for the moment, let's leave it there. Then there is a second step, which is to get the BV compactness. And the BV compactness is the point in which you are going to use the rigidity argument. So here, you need a rigidity argument. But BV is far from what you want, so the third, the very delicate, important step is to get SBV 0. And this is based on local lower bound alla Lauteri-Lucaus. So essentially it uses the local bounds proved by Lauteri-Lucaus in order to show this property. You localize this argument and you get this SBV0. I'll show you. I mean, this is too vague to be convincing. Okay, so let me start with step 2. So I start with 2. Okay. So in order to start with 2, so in 2 I will do something different from what I'm supposed to do here. So suppose that my energy is the following. E epsilon tilde of A epsilon. So the first term is almost the same as the other one. So the integral over omega of the distance squared of A epsilon from SO2 plus so the first term is almost the same, apart from the fact that I'm integrating everywhere, but doesn't really matter because I can always change my field and put A equal identity inside the set B epsilon of S, and I get the whole omega, right? The identity at 0 distance from SO2. So the changes are in the second term. So in the second term I put the total variation of the measure car epsilon, car A epsilon. Okay? So I take the measure Carl of A epsilon and I put the total variation. So, and assume that my field has bounded energy. Okay? So let me prove the BV compactness for this field with this assumption. I spoil the fact that the first step will be to change the field in order to compare that energy with this energy. Okay? So what is the first remark over here? Well, from this bound, you have that the integral of the distance squared of omega over omega of A epsilon from SO2 is less than m epsilon, so this goes to 0, and the curl of A epsilon is equibounded. Okay? So, if there the curl of A epsilon is 0, so if this is 0, this is a gradient, this is telling me that A epsilon should converge to a given rotation. Because this is a gradient, the distance converges to 0, rigidity. So this is telling that A epsilon converges to a constant rotation, in L2 actually. But this is not good enough, so this is too rigid for what we want. And so the way you do it is essentially using rigidity, right? So because this means that A epsilon is a gradient of something. You put it here. Each one of it has a constant rotation. So this set of rotation, so this is a finite dimensional problem. So you extract a sequence for which this rotation converges. This proves that this is the limiting rotation for this field, right? So proving that this gradient is close to a given rotation allows you to show that globally, when this goes to 0, this gradient converges to a given constant rotation. We don't have this estimate because we don't have a gradient, okay? And we don't even want this limit. So this is telling you that this incompatibility should be there if you really want to see an interface. And so what do we do when we don't have a gradient? Well, you can improve these rigidity statements. And show a series of rigidity estimates for incompatible fields. So let me state it in general. So this was stated in RD. So I also want to state it in RD. So I take omega in RD. And one can prove that if you have a field which is not a gradient, but for which you know that the curl of A is a measure, then there exists a constant, still depending only on omega and scale invariant, such that so for all A in L1 with this property, there exists a given rotation such that you can estimate the distance of A from this given rotation in L1 star. 1 star is d over d minus 1, right? With this constant times the distance, the L1 star norm of the distance of A from the rotations, plus the curl of A. So essentially, you have to correct this estimate in order to account for the fact that your field may not be globally a gradient. So if you have defects, you almost have rigidity, but you pay your distance. Somehow you pay with your distance from a given rotation with the amount of defects. If you too many defects, you are far from a constant rotation. Okay. So this rigidity for incompatible fields has a linear counterpart, which I didn't mention over there, I should have done it, which is the Korn inequality. Okay? So the Korn inequality that was also mentioned by Pascal, it's much older than the rigidity estimate, is somehow in between, it's between Poincaré inequality, if you want, and rigidity. So it's telling you that you can estimate the distance from a given skew-symmetric constant matrix of a gradient with the only symmetric part of the gradient, right? So the linear counterpart of this is the Korn, which tells you that you can estimate A from a given M, which is Q-symmetric, constant, with, again, the L1 star norm of the symmetric part of A plus the curl. Again, if you have curl equals 0, so you have a gradient, you end up with a Korn inequality. So these were proved in dimension d equal 2 by Müller, Scardia, and Zeppieri in 2014 in a paper in which they study the asymptotic behaviors of an energy which is slightly different but still is related is a nonlinear energy in 2 dimensions which is related with the distribution of dislocation of defects, and in general dimension by myself and Conti in 20-something, 23, I don't remember, but it's so recent. And instead this one was even earlier than that, because it was like a Korn in a sense, because it was proved in a paper in which we were doing linear elasticity with effects. And so this was a paper by Leoni, myself, and Ponsiglione. Oop, 12, I don't know. And again, I mean, Conti and myself. So this is the same, as actually is a Conrendu. So it's not a very, so to be honest, D greater than or equal 3 is not that difficult, because the key ingredient is a very nice result of Bourgain and Brezis. So it's just a matter of decomposing your field in a curl-free field and a divergence-free field, and use a regularity result of Bourgain and Brezis, and then use the classical. So the dimension 3 argument uses this Bourgain-Brezis tool, which is also used there, but in dimension 2 is more delicate. Anyway, so these are the key ingredients. In particular, if D is equal to 1 star is equal to, so we really have, if you want, we really have 2 objects that control the distance from rotation, which we know how to control. Okay? So now I'll show you how we use this. So this is a quite, say, standard argument, localization argument, how we can use this rigidity locally. So the first fact is that, of course, you can always extract a subsequence. So we assume that this field converges weakly in L2. Okay? And this is because you have, for instance, an L2 estimate using the first term. So, or if you want, because you can use this even better. You use this estimate globally in omega and you get a bound. Okay? So L2 is okay, but we want to get BV. So what we do is that we rewrite this estimate in cubes, in squares. So we take omega and we decompose omega in squares of size delta. Okay? So I call Qi delta a generic square over here. Okay? So for each of these square, I can apply rigidity. So what do I have? Recall that I need, so maybe I should, before doing the computation, I should tell you what is the idea. the idea is that I divided this domain in squares. Okay, in each square, I estimate the distance of my field from a constant rotation. So I don't want that in the limit the field converges to constant. I don't expect that. Okay, in general, this is not true. Okay, so what I'm going to do is to say that my field is close to a piecewise constant function which takes values in the rotations. Okay, and now I want to say that this piecewise constant function is bounded in BV. If it's bounded in BV, by compactness, I get L1 convergence, and if I get L1 convergence to something which is in BV, my field, the original field, converges as well in BV. So since I want a bound in BV, essentially I will have constant rotation, so I want to estimate the difference between two rotations in two neighboring squares, right? So I need an L1 estimate of this piecewise constant field. So I simply do an elder and get the L1. So what I get is that for each square there exists a rotation, which now I call R epsilon I, which is the constant rotation which I get from rigidity, such that the distance on my field from this constant rotation in L1 on this cube, okay, is, so this is my Euler argument, so it's estimated from above by the L2 norm L2, so times square root of the area, so 1 over delta. Okay? Okay, the area is delta squared, so if I do the elder, I have a delta over here, I put it there. Okay, so now this is estimated from above by rigidity. With essentially the energy, right? Okay, so it's a bit, so let me call eta epsilon of qi delta this quantity and gamma epsilon of qi delta this other quantity. So I don't have to repeat all this. So, so this constant does not depend on omega, but depends on cubes. It's a constant which does not depend on delta because it's scaling invariant. Okay, so this means that and the crucial idea, which is also the one that is used by Prisek, James, and Miller, for instance, to prove dimension reduction with nonlinear elasticity, is that you can reapply this argument to pairs of squares. Okay, and so now if you take a couple of squares. One is qi and the other one is qj. To each one you reapply the same argument and you will get a third rotation. Okay, and so the idea is that now you can estimate the distance of a given of this constant rotation with the one which corresponds to the neighboring pair, neighboring square. Okay, and so if you do that, you see if you multiply by delta this quantity, this is you can estimate from above this quantity with 1 over delta, the integral on qi Ri. So let me, for a moment, skip the delta and epsilon. Okay, I'll do it. Plus 1 over delta okay, so I simply do that, and now you see, so let me skip the computation for a moment. I think you'll believe it. So here I can increase putting also Qj. Easy. And now here I apply this inequality and this as well over here. Okay? So essentially I simply can estimate this by a constant times n epsilon of Qi union Qj plus gamma epsilon of Qi union Qj. Right? So I simply estimate this difference with this constant times essentially this energy over here. Okay? And now you see that this is essentially, and so once you have this, you can estimate this, you can do the same estimate. Where do I write all this? Okay, and so similarly, you can write Ri delta epsilon minus Rj delta epsilon times delta with a constant Did I convince you? So you can estimate the distance between two neighboring rotations, passing from a common rotation and using the rigidity. Okay? And so this is essentially telling you that if you define R delta epsilon, which is the piecewise constant function given by these rotations obtained with the rigidity argument, this function has a gradient, because the only gradient of this piecewise constant is the interface between two neighboring squares. So the gradient of this function is bounded by this quantity over there, which is the sum over all cubes, so which is essentially my energy, twice my energy, because I'm, I don't know, double counting the cubes or something like that. Okay? So a constant times my energy, right? Yes. And my energy is bounded. Well, no, it's not my energy, actually. It's more, no, it's not my energy. I wanted to make it short, but it's not my energy. It's better than my energy, actually. It's the integral over omega of the distance squared of A epsilon from SO2 plus the curl of A epsilon. So there is no 1 over epsilon over here. And so this means that this is bounded. This goes to 0. This is bounded. So this means that this is bounded. And yes, this is bounded. And so this means that I can extract a such sequence such that this converges to, in L1, to a function R delta, which belongs to BV now. And by law of semi-continuities, also this sequence is bounded for all delta. So I can extract a diagonal sequence or another subsequence such that this converts to L1 to a given function, which is now a BV function with values in SO2. And so the fact that these values is in XO2, so I will show you it in a minute. So, and then the next, the last, if you want, the last observation is that if you now go back to the first estimate over here, what you get is the L1 norm distance. So you sum all of these estimates over the cubes, you get that this is less or equal delta times something which is bounded. So it's the L1 norm is delta times this, which sum to something which is bounded, so something that is bounded. So this is telling you that when epsilon goes to 0 and delta goes to 0, epsilon minus A epsilon tends to 0. Okay? So at the end I think I have done. So I proved that this weak convergence becomes strong in L1 and the limit is BV because we use this standard argument of showing that if you are close to given rotation locally, you can reconstruct, if you want, you can approximate your field with something which is piecewise constant for which you control the BV norm. Okay? Okay, so this was more or less the best I wanted to do. And a last important step, now look at this weak, again, this weak, so this estimate over here, or maybe this one. Okay, so actually this is essentially a localization of an estimate that tells you that you can control your gradient in BV locally with these two pieces. This one tends to 0 because of that estimate over here. Okay? So essentially, if you neglect for a moment this, you are saying that you control your BV norm of this piecewise constant field with the curl of A epsilon. And in fact, you can push forward this argument and show that putting together all this argument, you can also prove that the total variation of A, even though you still don't know whether it's concentrated on jumps or not, but the total variation on A is controlled by the curl of A as measures. Okay? And this is the crucial step in order to get the SBV0 regularity, which though requires a more, say, complex or deep argument, a deeper argument. So let me give you just a hint because I don't have time to say much more than that. And okay. So the hint is the following. So let me introduce this notation, which is quite standard. So let me call mu epsilon the energy density, my energy density of this one, or no, maybe the original one. So times Lebesgue plus 1 over epsilon the characteristic functions of B epsilon over SA epsilon times Lebesgue, right? So since I assume that it's bounded, this converges weakly to some measure mu, and also let me call nu epsilon of A epsilon the curl of A epsilon and let me call nu A the limit, the weak limit, okay? So and then assume that epsilon is harmonic. I will not be able to say why this is important, but and assume that the curl of A epsilon is bounded from above by a constant times the characteristic function of this set as epsilon over epsilon. Then there is a very nice deep lemma by Lauteri-Lukaus, which says that there exists a delta 0 such that for all radii r, such that the ball of radius 2r center, so and for all x in omega, such that the ball is contained in omega, you can find a radius which is between r and 2r. I mean, the details are not that important, but let me state it in a proper way, such that the measure nu A the measure curl of A in B R bar of x is controlled by a constant times a function of this ratio, mu of B R of x, 2R of x actually, 2R of x over 2R times mu of B 2R. Okay, so what is it saying? And this function omega of t has the following behavior: is the logarithm of t to the minus 1 if t is less than delta 0, and the logarithm of delta 0 to the minus 1 if t is greater than delta 0. So essentially it's a function which starts with an infinite slope and then is constant. Okay? So let's see what this lemma is saying. So this lemma here is saying that you can estimate your measure of the your curl measure locally with a function of the limiting energy density, with a function that is so defined by this quantity here. So let me do an experiment over here. Let me divide by capital R over there, or twice capital R. And let me divide by 2R over here. I mean, they are comparable, so up to change the constant, I can do that. So you see that I have something that resembles the one density of this measure, because it's the ratio that is able to compute the density 1 of this measure, with a function that depends asymptotically on the one density of this measure, but is not linear. Okay? And I tell you that, I mean, this function omega t times t behaves like this in 0, okay, as a horizontal tangent. So what you get from this estimate, I don't know whether you believe me or not, what you get is that if you pass you get, I mean, and this implication is not immediate, but that if you call S the support of the curl of A, you prove that this S is contained in the set in which the one upper density of mu is positive, where the one upper density of mu is the lim sup of mu b rho of x over 2 rho. Okay? And this is exactly due to that. So essentially the idea is that when you are in a point in which this density is 0, this forces this quantity to go to 0, because you have something that behaves more than linear at 0. And this is essential because this set here is a one, in general, rectifiable T-fiable set. I'm missing the spelling of rectifiable in this moment. Okay, and this is generally this is a general fact. Okay, this set can be written as the union of sets, the intersection of sets, the union of sets that are one rectifiable. So this is one rectifiable. This means that the set S is one rectifiable, and so this is telling you that the measure total variation of A is controlled by a measure whose support is one-dimensional. So this means that this is one-dimensional, but this is a BV function, so it has in 2 dimensions it has a one-dimensional part, an intermediate part, and a 2-dimensional part. One-dimensional means it's only jumps. So this implies A as BV. 0, only jumps. No diffuse and no counter. No Lebesgue and no counter. Okay? Okay, well, I'm in this stage in which I cannot do much more. So let me just say that, so I didn't say anything about the refinement. Well, essentially, here you have to work a bit, quite a bit, but it's somehow hard job, but not particularly new, to change your field A in order to fulfill the assumption that allows you to use step 2 and step 3. So for step 2, you have to show something like the assumption that is here. So you have to show that your field can be sort of truncated, and then you can construct it in a way that the curl is bounded by this constant in its support. And so this somehow, you see that this assumption makes a clear connection between our energy, where is it? Over our energy over there, you can estimate it from below with this other energy, right? Instead of the measure divided by epsilon, you can put the curl. Okay, and then you have to show that if you can, you can change your field with an harmonic field, and you simply decrease the energy by a constant. So you lose constants in this argument, but this is a compactness argument, so you don't really care. And this losing constants is exactly the reason why the Lauteri-Lukacs argument doesn't have a match of the upper and the lower bound. To do that, you really have to work using the techniques in gamma convergence, localization, and so on, in order to see that the soil problem formula can really reproduce the gamma limit, so the lower bound. So let me finish with an observation. And the observation is about, if you want, the criticist the criticism of this model, which is a good model for small angular grain boundaries. Okay, so we produce an energy density, which is this one, which has a precise asymptotic formula to be defined, which has the right behavior at 0, but which has a very big defect if you want to use it globally. And the defect is the following, that this energy doesn't really respect the crystal invariance. Quindi so what do I mean with this? So let me do this experiment. So I have a lattice then I have an interface, and then here I have this lattice. With my continuum variables, this would correspond to take, for instance, identity over here, and rotation by pi over 2 over there, right? But then I recall you that the lines do not exist. There are only atoms over here, right? And clearly I don't have an interface. Okay, so this variable with large rotations, fake, some interfaces that do not really exist. So there are interfaces that are the ones, if you want, in this model, there are interfaces that are the ones that are between angles that are in the same equivalent group, if you want, with respect to the point group of the lattice, that are not interfaces. So the right energy density then should be another one which, given two rotations, say that you call G the group of symmetries, or I mean, group of rotations of so how do you call it? Group of invariance group of invariance variant group of the lattice. So in this picture, G would be simply rotation by pi over 2, so it's identity pi over 2 pi, etc. Okay, so what I simply should do is take my energy density and minimize it among all possible choices of this rotation. So I take my energy density, but instead of looking at the interface between R plus and R minus, I take any possible rotation of R minus, for instance, where G belongs to the group. Okay? So this means that this energy would give zero energy to this interface, right? And so then I would take a new model, which should be similar to the other I've seen before, but with this new energy density, with the features that we had before, with the small angle grain boundaries, behavior, and so on. And A, at this point, I can still take SBV 0 with values in rotations, because after all, this will not take into account interfaces between, say, objects that are in the same equivalent class, or directly I can use the set rotation quotient G, right? And so where I can make sense to this set using the notion of BV and subspaces of it with values in metric spaces introduced by Ambrosio in the 90s. Okay, so the advantage of using this framework, where here I put this nice metric space, is that in principle, I could also be able to justify a model like that with an approximation. So, because not only this is well defined, but also H1 with values in 2 by 2 matrices, quotient G is well defined. Okay, so in principle, I could find a good model, a diffuse interface model, okay, a diffuse interface model that produces in the limit this energy over here. And so this is the point in which I cannot really go because I don't have time, but so I have just 5 minutes and I show you this for a reason that is sort of so we don't know how to really do the analysis of Lauteri-Lukacs with this new framework. Essentially because in these spaces, so the reason why I show you this is, you'll understand it in a minute. In these spaces is kind of natural to give the notion of modulus of the gradient, but it's not that clear what is the curl of something, okay? So the equivalent of the Lauteri-Lukacs energy is still not clear, okay? So the model that contains physics. So that's the reason why at the beginning I said, okay, there are diffuse interface models that contain the physics that are meant to be a derivation of the model, and then there are other models that contain less physics that are maybe meant to be approximation of your model, a good approximation of your model. And this is the case of the Ambrosio-Tortorelli type energies, okay? So, which can be used instead in order to prove or show some segmentation of images. So I don't really tell you anything about this, but we have studied a model which is an Ambrosio-Tortorelli type model in which it appears a gradient, a regularizing gradient, which is able to reproduce an energy of this type, and this has been done in collaboration with Sergio Conti, Vito Crismale, and Annalisa Malusa. And the reason why I want to show you this picture is because I don't know whether somebody said that, but Monday morning Bob Cohn passed away. And this problem was pointed to me by Bob Cohn some years ago. So I really want to say something, I really want to give a personal memory because he was a very special person. So he passed away after a long illness. He was a very kind person, courageous and that. And I mean, I spent 2 months in New York. Roberta did the same last year. 2 years ago, he was already very ill, but was very nice and always available, and was a very discreet person and still helpful and profound. So I wanted to remember him in this occasion. So with this, I think I stop.